I think we're good to go. So once again, welcome everybody to this month's edition of the MLOps reading group. Good to see everybody joining. I see a lot of familiar faces, a lot of new faces. I think it's very, very cool that we have people from all over the world, again, covering all the time zones from all the continents coming here for one common goal, just to, dive deeper into AI, machine learning, and just demystify this whole thing. So it's good to have you guys here. And today's session, and I see Waldemar's cat's making another cameo. I love it every time. Brilliant. So today's session is a little bit special. Why? Because we have the source of the paper right here with us. Usually how we do things is we shortlist a bunch of cutting-edge technical papers released very recently, and we send it on the public Slack channels for people to vote and to weigh in on what are people interested in talking about. And people usually end up voting for one paper. But this time, things were a bit different. Lihu's paper, this paper won by a landslide. A lot of people wanted to talk about it, and I was very intrigued by that. And I wanted to see who's the author, and I reached out to Lihu, the author, and he has very generously accepted to join us today and answer our questions and just take us through the thing. So that's what makes the session special today. So if you guys have any questions whatsoever at any point, we know the person that wrote the paper. He's here with us, so feel free to ask any questions. And as usual, we have our amazing host today joined. So let me give you guys a quick intro. As usual, we have a familiar face returning in Corey Jones. He's a senior ML engineer at Chick-fil-A. Always a pleasure. And we have Sophia from Skoronsky. I suck at names.
That was
I hate it. Do you mind? So Sophia is joining us today as well. She's a data scientist at Breckenridge Capital, and as usual, we have Waldemar Eggerson. He's a AI team lead at Smart Data, and also, last but not least, we have our amazing resource person for today, the author of the paper. He's a postdoctoral research associate at the Imperial College London, Mr. Lihu. So, without further ado, let me pass the microphone to Corey. Do you want to take over from here?
Sure, I will kick things off in a different type of way, and just thank you so much for the Lord. Like you're a rock star and champion of this community. My comments will be pretty brief, but I always I think it's important to just kind of level set, right? We've heard some people say that you're here to learn. This is a safe space. This is a place for us to learn and talk about this content. Some folks are coming with 10, 15, 20 years of experience doing things in a supplementary way, and like you are an expert in your way. And then there's other people like, listen, I have no idea what this was. I read this paper and I understood the first 3 paragraphs. The rest of it, I have no idea, and I have all these questions. We have a wide range of people, and we want to let you know that that is A-okay. We want to celebrate everyone, the experts, the folks that are just starting, the people in the middle, and then the folks that are just like, I was curious, and I saw this was here. I like Dimitrios. I've seen him, and I've heard about this community, and I want to just kind of join and see what you guys are talking about. And so we want to make sure that this is a safe spot. Ask questions. If you feel uncomfortable, ask them verbally. Drop it in the chat. We'll be there to kind of observe and listen in. And it is okay if you say nothing. It is okay if you ask a lot of questions. This is a good place for us to come and learn. And that is part of the heartbeat of the reading group for the MLOps community. We get to learn. We get to grow together. We get to have a little bit of fun. And so I wanted to just kind of sell this up right there and bring us in. I'm excited about this because I've been thinking about this type of content for this paper. And so I'm coming in as like a person in the middle. And so if you see me ask some crazy questions, that's okay. So let's celebrate that, everyone being able to come in and have some fun. So hopefully that lets you know who we are, how we kind of operate in that energy and that heartbeat of this. And so I'm pumped. I'm excited, but I'm also humble enough to know that I don't know it all, and that's okay. And so we want to say that to each of you all. It's okay if you don't know it all, and it's okay if you know almost all of it. So let's come in together and grow together. With that being said, I'm going to kick this over to the man with the master plan, the one who had the courage, right, to write a paper, publish it, do all of that research and all the things that are there. I'm looking at like the screens right to the left of me, and that is the one and only who. So I know you're going to get a chance and help ground us and give us kind of summary and perspective. And I'm going to mute my mic because I need to pull out my notepad because this is about to be good.
So regarding the motivation, I think this very interesting question. And when you ask me the motivation, then I started reflecting myself why I wrote this paper and why I stick to the small scale language models. And I believe that there are two motivations. And the first motivation is kind of still bit, but very direct. I stick to small models or emphasize small scale language models since I don't have very many powerful GPUs. I don't have the computing resources. So I have to admit that compared to the industrial giant, and we have less computing resources. And given my personal experience, while I was doing my PhD, I remember I had 2 research projects going at the same time. And the first project is about positional encodings. And I'd like to inject the word ordering information into attentional modules. As we know, the attention itself, it cannot capture the word orderings. It means that they are position independent. And in this project, we need to study the properties of different position encodings, and we like to pre-train word-based model from scratch. And in my lab, I have 4 100 cards, and it took me more than 1 month to pre-train the birth model from scratch. And I need to repeat these experiments many times. And due to this reason, this project was very struggling. Every time I submitted this paper, and there was some concurrent findings, and it means that I need to include these new findings in my current version. And it was rejected many times from ACL to iClear. And finally, I got some negative comments regarding this submission. And the reviewer said, you should study much larger models like Llama 7 billion instead of BERT and Robert, since their size is fixed and is small and it's not a trend. So through this, I realized I cannot compete with people that have more or much powerful computing resources. And this lesson I learned from this research project. And another research project is that I try to fix the issue of BERT-based model. For the encoder-only language models, they have an issue when fitting with the out-of-vocabulary words. It means that these words they have never seen during their pre-training. So they tend to make mistakes when fitting with these out-of-vocabulary words. So I propose to use a small model. It's like a plugin. So you don't need to pre-train the original model from scratch. You just need to fit a smaller, tiny model that can impute embeddings for unseen words, and then you make the 2 sides of model work together. Then you can fix the auto-vocabulary issue. And after the paper was accepted by ACL, it's an oral paper, and also I got some messages that people are very interested in this direction, how to use small models to enhance larger models. And this is the first thing that or lessons I have learned. And recently, why I started writing this survey paper, actually, is from some complaints. Almost every day, I can hear people they are talking about how powerful and how great LLMs, and at the same time, I can also hear from my colleagues or friends or people in this field, they are complaining. They say that the LLM field is dominated by these high-tech companies, by Google, by OpenAI, and we cannot compete with them. And I heard this, I keep this in mind. And a direct stimulus to this paper is the work from OpenAI. They published a paper named Weak to Strong Generalization. And the main or core idea is to use a smaller model or a weak model to supervise a larger model. So from this, I realized that small model can also contribute to LM. And this is the first point. The second, this spring, I traveled to Malta for NLP conference. And I saw a paper. So they try to use small models to enhance in-context learning. So for in-context learning, you gave a few examples, and then the LM can learn these new things in the context, and then can be applied to unseen or new tasks. And I saw a research, they try to use small model to generate or to label the input samples. And through this way, they can inject knowledge into the context. And their theoretical is kind of sexy that small models can dance, or small models can help LLMs. And after that, I went to my advisor's office. My advisor is a kind of article, and asked him whether we should start this project to think of how to use small models to enhance LLMs, and what is the role of small models in the area of LLMs. And this, I know for some users, they don't consider the cost or the expense. They stick to ChatGPT or Claude, to large-scale models. However, for some simple queries, for some specific scenarios, we don't need such large language models. And I think maybe we should inform people or tell people that for some certain task, we don't need larger language model. We can still use simple ones. And this is optimization for the resource usages, for power, for our environment. And starting from this point, and I wrote this paper. I think this motivation. Regarding the overview of this, maybe I can also present this briefly. So the basic idea is that LLM are very powerful. We all know this. But I did a very interesting study. I like to know which NLP model on Hugging Face is downloaded most. And then I crowd data on Hugging Face and do the statistics. And the interesting thing is that I found the smaller model is still widely used. It's just more popular than the larger counterparts. And the most popular model is still BERT-based model. So this raises an interesting question. What is the role of small models in the area of LM? And to assess the role of small models, nice cat. To assess the role of small models, we need to analyze the strengths and the weaknesses of both small models and the larger models. So for sure, for LMs, they can achieve state-of-the-art performance across various tasks. And also they can be generalized to an unseen task, to new task with minimum examples. This is the strength of LLMs. And what is the weakness? What is the flaw? And a clear one is that if you want to to use LLM to pre-train, to fine-tune, or to deploy this model, you need computer resources. So this is the one limitation. Another one is interpretability. So based on our intuition, smaller or shallower models, they are more transparent. It's easy to understand their internal process. So they tend to be interpretable. So we are considering, so maybe for some certain scenarios, small models have their niche market. For example, for the healthcare, for the legal question answering, and we need a explainable model. We need to know the reasoning process. If the model gives an output, we need to know why it gives such an output, not that. So for the interpretability required environment, we need small models. Another classic scenario is the computing resource limited scenario for edge devices for our cell phone. If we want to deploy a language model, maybe a tiny model can work. So this is the view of the computation. And also, small models and the larger language models, they can co-work together and for optimizing the resource usage or to have better performance. So maybe the two sides of models, they can complement each other's shortcomings. For example, I would use my studies to showcase this. So a known issue of LLMs is that they may generate hallucinated text. So a potential solution to this is that we can estimate the confidence or the uncertainty of their responses or their answers. This means that we ask them to express uncertainty in their generated text. I say that for 100% sure this is this case, or I'm not sure. I didn't remember this correctly. I'm 50% sure, or I've never seen this. I don't know. I have no idea. So we can add this uncertainty in their answers. To do this, we can use a small model to measure or to estimate the LLM generated text. So this is one way how LLMs and small models do the collaboration. And the second scenario regarding the computation, I would like to emphasize my study about the short text reasoning. So for short text, like the stream matching, I guess you all know stream matching to compare the semantic similarity between short text.
But I do wonder, like you mentioned that interpretability is clear or explainability is clear for small language models. And I do know that for small machine learning models like this, that is very clearly there. But for like small language models, which are still relatively large neural networks, I don't fully understand what is explainable about them. Can you go into more details on that?
Sure. Yeah, you are totally correct. For the tree models, we can offer some linear models. It's very easy to understand. And the intuition is that I'm sure there's no clear definition or clear things that a bigger model share a better interpretability than a smaller model. But intuition is that for the shallower, we have limited layers. Imagine we just have one layer. Or for llama, we have very, very deep layer. So it's hard to interpret the internal process. This is the intuition.
Great, thanks.
Yeah.
We have another one, if you don't mind, Liu. This one's from Dinesh. He asked, would uncertainty be text, which is part of the output, or probability scores across all tokens?
It can be both. So first, we can ask them to express uncertainty in their text, like our humans. You ask me a question like maybe So when audience raise the question, so I don't know, I just say I don't know. But for LLMs, we force them to generate answers for any query. So one solution is that apart from the generated text with regard to the query, you can also generate a confidence score or a verbalized thing to express the uncertainty score. Like, I'm very sure, or I don't know, I'm only 50% sure. So we can use prompt, like, give me the answer with a confidence score in your response. We can just use this prompt-based method to elicit confidence score. This is one way. Another way is that we can. So imagine. I like to use this comparison. Imagine if you want to check whether a person is lying, so you can ask the same query to the person multiple times and check whether his responses are consistent or contradicted. Through this way, we can compute a consistency score. We use this as a confidence score. So first, we can ask them to express uncertainty by themselves. And the second, we can observe their external behaviors to get these confidence scores. And another fancy way is that we use their internal signals. Like, if you want to check whether this one is lying, you can detect their brain activities or their blood pressure, heartbeat. So these internal signals. Also, it can be applied to LLMs. We can check their internal activations or the probability distribution over the vocabulary. So there are many ways to get the confidence scores. And what is the role of small models here? The thing is that you can use a small model, a fine-tuned one, to check the consistency, to check whether their responses are contradicted with each other. I hope it's clear.
Yeah, that was great. Thank you, Leitu. I think Sophia and Waldemar, I think, would be able to give us some thoughts as well. But before that, we have one more question from Keith. Do certain kinds of research in SLMs generalize better to LLMs? Are there certain kinds that don't generalize well? Your work on functional embeddings seems like it would generalize well to LLMs.
Yeah, I would say that in general, larger models are more generalized compared to smaller ones. And the benefit of using small models is that for very specific tasks, for example, for tabular learning, or for short text reasoning, or for domain-specific tasks, if you fine-tune a small model on limited data samples, and it can outperform a general-purpose large language model. But regarding the generality, in general, larger models are better. And I guess also he asked the positional encodings.
I can speak up. I meant about the generalizability of the research, not the generalizability of the model.
Mm-hmm.
Like when you learn something on with positional embeddings by doing research on small language models, you can expect that research will hold true as a larger language model, but certain kinds of research may not when you scale up.
You mean dedicated to the embeddings?
Like the embeddings, or for instance, different types of attention mechanisms may work on small but not on large, or work on large but not on small.
Yeah, but my experience that even though for embeddings, my experience that larger models still better.
Yeah, so the idea is to just look at the paper together and correlation parts and say a few words about each part and maybe spark some discussion. No, I don't hear anything. Can someone say something?
Yes, can see the
Yeah,
paper.
we can see it. Sorry.
All right. So, yes, it's a bit different now since we have the author here to present it, but usually we would just go through the paper and discuss things that stood out for us, maybe get some different points of view, and ideally talk about it. Whenever there's a question or idea pops up, we can maybe have a little chat. So, no need to introduce the motivation or the concepts. We can just go right into it. So, there were two different things that so in this paper we viewed it from two different aspects of collaboration and competition. We're going to focus on collaboration for now. So how can they enhance each other?
There's a question from Isaac, right? Isaac, you want to?
Yes. Just on that very first graph, the Hugging Face downloads,
Yeah.
do you think that might be because for larger models, people would tend to use APIs instead of downloading them and self-hosting them? So that might not necessarily be an indication of model popularity because we're not seeing the usage of the larger models in that graph.
That's my intuition. I don't know. What do you think?
As it can be, so we overlooked some downloads from API, and but in general, also my gut feeling, or you can ask people around, who for most applications we still stick to the BERT-based model. I think this finding relatively fair enough.
Yeah, was this for like 1 month or average over a long time, or is it just like
Per month.
August, July this year?
Yes, you can collect it on August 25th. So by month.
That's interesting. Yeah, for me, like I used to use BERT and Robusta when I was like 3 years ago.
3 years ago.
I was also wondering at that level, like maybe if you're downloading such large files, you're gonna keep them on your local machine once, and then if you're downloading the smaller ones, you might be like, oh, I'll re-download it every time. Like it's not that much effort.
No.
So I think you're
Yeah, can be.
All right, so we can maybe look at this picture here together. It shows the kind of, like a mind map tree of the whole thing, the paper. So I'm going to focus on the first 5 items here. This is how small models can enhance large language models. There's data curation and weak to strong paradigm that you mentioned earlier, which have to do with how to train a large language model effectively with the help of small models. And then we have inference, evaluation, and domain adaptation, which is, maybe of more direct interest to people who are not training the models, but just using them, applying them. And to some notes, we'll have some highlights to point out and throw out questions whenever you can. So the first topic is data curation, and the motivation for that is that we're already training our models on the entire internet, and that's proven quite fruitful so far. But is there any more text left? Like I thought it was super impressive when these smaller models were trained on the whole of Wikipedia and all the books in the world. But then GPT-3 came out and etc. And it goes on and on. But recent research supports the notion that less is more. This is the main thing here, that you can train on a much smaller set and get a high quality language model out of it. And I remember one paper this year or some study about textbooks are all you need or something, where they trained only on like university textbooks or all textbooks in the world to get a kind of smart model instead of just using all the data on the internet. This is a bunch of nonsense. Selecting it properly is key to getting a powerful yet maybe effective or like efficient model. It's not the biggest model I've worked. And there are heuristics for selecting data, for filtering out the nonsense, but we can also use the smaller models. And a simple classifier can be trained to assess content quality. It did that, I think this is the GPT-3 paper, and in subsequent papers where they trained large language models. And yeah, so as a pre-filtering step for curating it, we can run it through the BERT model that notices that a tweet is not as useful as a paragraph from a scientific paper. There's also reweighting, which I thought was pretty cool. It's like affecting the sampling of different sources. So we could use a model especially for weighting the samples. So we would, I guess we would weight something that comes from Wikipedia higher than what comes from Twitter. And what do you think about this? Any comments? So we have, I think, there was like a recent line of models came from MIT or something, 1 billion parameter or a few billion parameters, which were scoring as high or higher than models that were much bigger that came out earlier. So this is one tool we have to compress the models into
one thing I think I read in this section somewhere is like that you could use it to filter out like toxic language and this kind of an interest. And I was wondering, how do we handle like the fact that the LLMs, you don't want to train them to create toxic language, but you do want them to be able to handle if a user would use toxic language against them. Is there like a technique that we use to make sure that they're still able to do that if we remove the toxic language from their datasets?
I think that might have to do with the instruction tuning. Like, I think how I did it with GPT-4, for example, was just have people do reinforcement learning from human feedback. They were like humans reading all the toxic materials, the toxic responses, and flagging them. And then that's used with some reinforcement mechanism. So that's my idea. I don't really know the answer, but that's what I think. If someone else has some wisdom to share, maybe.
I think there might be other ways, like this might be the way that it is done, definitely. I don't know. There might be ways of like also like subclassifying in there and asking like, is this like actual toxic generation or is this text responding to toxicity, and maybe training on the responses that are detoxifying would be interesting maybe.
I think there are already existing work they train a small classifier to determine whether the seed sample is toxic or not through this way to filter out. And I also mentioned this in the, maybe there is a future direction part, and a finding reveals that if you remove some toxic content, it can decrease the performance of the original model. But I don't know the exact reason.
Cool. So the same principle applies to the instruction tuning. So we can, just like we can select the pre-training data, we can also select the instruction data. So the study less is more for alignment demonstrates that fine-tuning on just 1,000 carefully curated instruction examples can yield a well-aligned model, I guess. Model. So yeah, these are the two main steps to build an LLM: pre-training and instruction fine-tuning. So that's super useful. However, maybe like not directly useful for engineers, except for those who are working on developing these systems. And similar to this is the weak to strong paradigm. So I thought, when I read this, I was a bit confused at first. I thought it was kind of about, I could understand how a weaker model could like teach a stronger model, but this is about the alignment with human feedback to, I guess, not say that, use the toxic language or whenever we talked about earlier. And this is something that has recently been shown, and I think we mentioned earlier, so OpenAI did this, that we can, okay, so this scenario introduces a new paradigm for aligning superhuman models termed weak to strong generalization, which involves using smaller models as supervisors for larger models. So we could have, I think, often a set of different like specialized models, one for maybe if they're teaching or trying to align the larger model with different things that are important. And that seems to work. And the motivation for this is that, yeah, you can't just have a human judging the output of a superhuman model. So we need to have some automated way to scale this up and continue into the superhuman era. I don't have much to say about this, but
Because
this, sorry?
the traditional approach is the upper way around, like where you, or like the first thing that people did was have a stronger model and then try to train smaller models based on the supervision of the larger models. But so this is flipping it around, or
Yeah,
Yeah.
we go into knowledge distillation later on in the paper, so which is the large, the small.
Is it about the alignment mainly? So maybe, Lihu, could you share some, like maybe explain the basic idea on this?
Weak to strong paradigm.
Yeah.
Okay, the basic idea is that OpenAI thinks that in the future we can have superhuman models. That means that their capabilities are more superior than our human, and also for some specific task, for example, for code generation. So a very powerful model can generate complex, lengthy codes. It's hard for our human to do the annotation. This is too long, too complicated, and also contains some logics. We don't know whether there are some risks or some privacy problem or safety problem. So here we need to introduce another model to supervise or to their idea is kind of easy to understand. She just used a weaker model, smaller model to generate pseudo labels for these training samples, and through this way to supervise the larger model, and the prove that it can work. So this is I think the basic idea of the weak to strong paradigm.
Yeah, thank you. So yeah, this is a very interesting and relevant topic related to the alignment problem, and are we going to continue, 3-4 years from now? And then a small model doesn't necessarily mean a BERT model in this context. It just means smaller relatively to the large one. So we could have GPT-4 assessing helping to tune, making GPT-5 more aligned with human values. That's the idea, I guess. Then we can move on to the next part, which is about efficient inference, and it's maybe most related to MLOps or this kind of operations of using these models in production. And yeah, I guess the idea is that we can use smaller models when they work. We can combine them. We don't need to always just use the sledgehammer when we can use a hammer. Personally, I tend to just use the GPT-4 API, or for me, maybe not. When it's actually just like a classification task for which maybe a simpler model exists. And that doesn't really matter because I'm doing it 100 times or 1,000 times, and maybe don't care so much about 100 cents. But you do it 1 million times, it starts to count. So there's different approaches. So overall, it's modern ensembling. So ensemble methods are just combining different models. You can have a voting mechanism, maybe see when they agree, and often get a better performance than individuals. Like random forests are just ensemble decision trees, for example. And there are two different categories. There's a model cascading, which I thought was pretty cool. It's similar to, I guess, if you talk to some organization or company, you first talk to the customer support and they can probably answer your question. And then they raise the issue to someone higher in the chain and maybe ending with an expert. So similarly, we could first use a small or like medium large language model to address an issue, or try to solve a task. But if it's out of that model's capabilities, we cascade it up to the more powerful one. And the critical step in this process is determining whether a given model is capable of addressing the input question. This method effectively optimizes inference speed and reduces financial costs. There are multiple different approaches. So we have citations here for 2024 for techniques for training a small evaluator to assess the correctness, confidence, or quality of a model's output. And like if that's possible, I don't know how well these approaches work, but it's great at least to have the confidence. So if you are using a prediction to guide some decision, if you have the confidence as well, that it's 60% confidence or 95%, it changes everything. But how valuable the prediction is. I can't go into the details here since I didn't read these papers, but sounds like an interesting thing. They employ verification prompts. Yeah, I guess it's just prompting models specifically for doing this kind of evaluation, maybe trained specifically for that. And the other approach is model routing, which is about routing or forwarding the input to the right model. Then we need to predict it somehow. And preferably without computing the output of everyone and doing it afterwards. We need to predict it somehow in beforehand to know which one to choose. So I guess, you can have some heuristics for it, like if it's a really long input, you need to use a model with a long context window. If it's about reasoning, seems complicated, you can maybe use the chain of thought model. And there are different examples here. One cool one here, just to mention something, FORC. They propose a meta model. Cool term here. No, it's just a regression model. It's just some kind of predictor to assign queries to the most suitable model without requiring the execution of any large model during the process. The meta model is trained on existing pairs of queries and model performance scores. So, yeah, if you have something like this, I can predict which model to use. Then you can have this kind of society of different models. So maybe more similar to natural intelligence, how it works in us, to have like different things responsible for different like specialists. And speculative decoding is similar, except it's about having a small model help the larger model generate tokens. Sorry, I don't know if I can explain it. This is just something I read. I think this was all kind of cool. I haven't tried using any of this. Has anyone in the room tried using ensemble methods? Instead of just going straight to the sledgehammer.
I think it is interesting because I feel like in more traditional machine learning, you would often ideally start with a very simple model and then slowly build up. And then when you build up, you can maybe start building an ensemble based on like all the models you had on your path. But I feel like with the LLMs, because the easiest, simplest, quickest approach is to just send it to the big LLM, you end up like starting straight off with the most powerful one and then starting to think, well, to decrease cost, we have to add other models. And it is a bit flipped around, this kind of process, I think, in this evolution.
We are doing a project at the moment using multimodal Gemini models to sort of validate whether images that people might upload to an e-commerce marketplace or adhere to certain rules. And interestingly, we have seen that depending on the rule, it's not always the biggest model that gives the best performance. Like sometimes the smaller model gives better performance for certain rules. But I guess as always with these LLMs, it's not very transparent or clear why that might be. So I just thought that is interesting. So we're evaluating all the different Google Gemini multimodal models, and some of them perform better on some questions compared to others.
I'll do my best to run through some of these last 5. I actually created a little slide deck because I have a bit easier time getting through this if there's graphics. Because I like Corey, I think I'm somewhere in the middle in terms of expertise, so I'll share like some of my takeaways. So let me just set up the screen sharing real quick. So the last 5 techniques, I think I wanted to start with this one primarily because it's first, but also I spent the most time here because I think a lot of us, if you're experimenting with LLMs, you are often running into RAG as a technique. For anyone that doesn't know, it's a technique that enhances large language models by combining them with an external knowledge base, and then retrieves relevant information and embeds it in the context of the prompt given to a language model, which allows it to produce more informed and accurate responses. Because as Lihu was mentioning, LLMs have known problems with memorization. And also hallucinations. So Lihu categorized these into 3 different, or the authors categorized the different RAG techniques into 3 different areas, textual documents. And so these are retrievers that typically don't generalize well, I'd say, because they require specific vocab needing to be present. But so I think some of us are familiar with things like term frequency, inverse document frequency, or BM25, best match 25, which is a ranking algorithm to determine relevance of a document to a query. And so you can kind of see a nice graphic of what sparse retrievers are versus dense, and using something like BERT as the encoder for queries and documents and doing some similarity matching is the dense retriever technique at a very high level. So let me just quickly move along, and feel free to interrupt again. So I didn't read all the papers, but I wanted to pull in some like high level graphics because they kind of show you other implementations of RAG using different LLMs. And in this case, some of them are using smaller fine-tuned LLMs as part of the retrieval process, I say. And so Knowledge GPT at the top was one of the highlighted applications. And so it uses something like, and all these papers have their own like branded prompting technique. So this one is called Program of Thought Prompting Technique. And so it generates search queries for knowledge bases, and then it has 2 tasks associated with it. It's the knowledge retrieval part and the knowledge storage. And since we're talking about SMs, oh yeah, and I guess I should back up. The small models in this case are the retrievers for RAG systems. And so retrieval for Knowledge GPT involves 3 steps. It generates a piece of search code, which you can kind of see in the yellow. Then the search code is executed to retrieve the relevant knowledge. And then the generated code, so it uses all of these things, and then is fed into the actual LLM to answer the input query. And so then just quickly moving around to TRAG. So it basically is a vector database plus an entities tree. For a given input user query, the vector database is searches across the vector document, vector database. It pulls in the relevant chunk. If there's any organization mention, it then queries across the entities tree to add that information to the context. And then it uses a fine-tuned LLM to generate a response. And then, so that's kind of some information. Oh yeah, and so these are using structured knowledge, meaning from knowledge graphs, from tables, or from databases. All right, we are so gone on time, so I'm just going to move ahead. If anyone has any flags, I'll share this in the Slack if anyone's interested. And then the other piece that's probably relevant to all of us, especially if you're using the API primarily, is using small models in prompt-based learning. So prompt engineering generally, as we know, is constructing prompts to guide frozen LLMs without parameter updates, and in-context learning is including a few examples within the prompt. So we could potentially use small models here to augment the prompt retrieval process or the prompt selection. And so I just wanted to show two examples that were given in the paper. The first one, Uprise, it tunes a lightweight and retriever that automatically retrieves prompts from a pre-constructed pool. So it adds a prompt to a given input. It prepends, I guess. And then it uses the frozen LLM to evaluate the prompt performance. And in order to train the prompt retriever, the obtained evaluation from the frozen LLM is then used to tune the retriever in a reverse manner. And then there's DistilBERT, which is a generator retriever which decomposes, which is used to decompose a complex prompt into subproblems that require fewer reasoning steps. And then the large model comes in to answer this expanded input, and it's called the solver large language model. So yeah, I guess you're just kind of moving ahead. You can use models to fix flaws of large language models. This kind of starts going into contrastive decoding that Valdemar started talking about, and one of the papers had a very spicy example that I wanted to talk about, but I'll just share it in the Slack. And then so you can use contrastive decoding, which is leveraging the differences between two models: a larger capable model, the expert, and a smaller, less capable model, the amateur. And the idea is to choose tokens that maximize the difference in log likelihood between the expert and amateur. So we're selecting tokens that the expert model finds highly probable. And okay, so I guess a useful point here is that contrastive decoding happens during inference. It's not doing any sort of training of or knowledge transfer. It's just using combined outputs to produce the best next term or highest log likelihood term. And so where that's different is, I think we're at time. So maybe I'll pause here and just see what everyone's.
I think you can just go ahead for a few more minutes. I mean, if you guys can just stick around. If you guys have no sharp exit at right now, you guys feel free to stick around. So just take your time, I guess.
Yeah. I'll probably, I actually have to run too, but I'll leave in about a few minutes. But so contrastive decoding happens during inference, whereas knowledge distillation is a training technique where you're training the model, larger models, like parameters, and transferring them to the smaller model. And so classically, this is how DistilBERT was created. And so there's kind of a nice graphic of DistilBERT here. So DistilBERT had full access to the internal architecture and parameters of teacher model BERT. And so the main goal of this is to, model compression and improving efficiency of the larger model. And so, so that was the goal here for DistilBERT as well. And white box knowledge distillation means that they have full access to the teacher model. And so to create DistilBERT, it initializes parameters during training. It initializes parameters from every second layer of the BERT model, and then it employed this triple loss function in order to generate updated internal parameters to mimic the output of BERT. So I think I've worked with BERT in the past for like college projects, but I don't currently use it. Again, I'm mostly large language model API user. And so Blackbox is augmenting, is still about transferring knowledge, but it's without access to the teacher's internal architecture. So only the outputs are available. And so the student model must learn how to mimic the teacher's output given the same input. So you can kind of do this through two techniques, or again, here's just two examples given. There's chain of thought, where you're transferring the reasoning abilities, specifically the step-by-step reasoning process, and that's kind of what's highlighted in this very tiny example here. And then the student model through training learns to produce similar reasoning chains and final answers. And then instruction following, and then is more about prompts that demonstrate how the teacher model follows instructions, which the student again learns to mimic. So the teacher prompts are typically, I was going to try and get an image here, but teacher prompts are typically more detailed and explicit, asking for, like step-by-step process, and the student prompts are simpler. So during distillation, the student model learns to produce outputs to the teachers, even when they're given simpler prompts. And then the last, I think this is the last one, right, is you can use large language models to generate synthetic data for small models to train on. And so this goes back to the point about human-graded data is finite that Lihu and Valdemar also brought up. And so there's, again, of course, two categories of data synthesis. So we have data generation, with some examples here, as well as data augmentation, where you can improve. You can possibly give more examples of using the same base text just by asking it to generate different alternatives. And I think this was flagged as one that you probably wouldn't use in a heavily regulated industry, like the medical field or finance, because I think for the most part, you always are trying to anticipate to get the same, because like I think in medical environments, standard of care is very specific to a timeline, and you don't want to alter any data that might change that information. Anyway, that's all I had. So we got through it all.
Wow.
Yeah, that was incredible with slides and all.
Yep.
Incredible. Yeah, that was super insightful. Thank you so much, Sophia.
Yeah.
I know we ran up on time a little bit, but honestly, everybody, thank you so much for joining. This was such a great session, and thank you, Lee, for all your contributions and insights. Very, very, very well done. And thank you for writing such a kick-ass paper, honestly. There's so much to go through. So thank you everybody for joining, and we'll see you next month, same time, same place, with a brand new paper. Hopefully we're gonna start with Sophia the next time, so she can show off her slides. But yeah, thank you so much everybody. Thank you, Valdemar, and thank you, Sophia, and thank you, Corey, for your contributions. See you all next time. Incredible.
Thank you.
Thank you, everyone.
Thank you. Bye.